And we have with the first problem, okay, we're looking at the domain as well as specified values concerning a given function for the first two problems. And in number one, okay, we have the function f of x is equal to the square root of x plus 11. And the first part, okay, we have in the leadoff problem, okay, so we're looking at the value of y whenever x is set to 25. So we have for this functional notation upon which we are referring to y, okay, we have in reference to f of x, so whenever x is 25, y is f of 25. And looking at the specific value, so we have in the setup, so we have f of the input is equal to the square root of the input plus 11. Okay, so we have with 25 as the input. Okay, so we have f of 25, okay, and that is going to be the square root of 25 plus 11. And we have 25 plus 11 is 36, which is going to reduce to 6. Okay, so for a point that is on the graph of y is equal to f of x is equal to the square root of x plus 11, we're going to have among them 25 and 6. Now, for what we have in the case of part B, and we have now looking for the y value whenever x is set to negative 7. So we have for f of negative 7, we're going to have the square root of negative 7 plus 11. And negative 7 plus 11 is going to come out to 4. And again, we have for the square roots of an expression, this cannot reduce to a negative constant. And in the case of the square root of 4, while there are two numbers that will square into like 36 as well as 4, we're only going to take the positive result. In this case, we have at 2. Now, regarding the domain of f of x equal to the square root of x plus 11, okay, so because we have an even root radical, we have the restriction that what is underneath cannot be negative. So we have, in looking for the domain, again, because we have a square root, okay, x plus 11 cannot be negative. And since we do not have a fraction that can create a potential for there to be a 0 denominator, okay, now x plus 11 can be 0 because we have f of x given in direct terms. So x plus 11, it can be 0 since you can have the square root of 0 as long as you do not have 0 in the denominator position. And also x plus 11 can be positive. So we have here x plus 11 is greater than or equal to 0. And in solving for x, if we take 11 away from both sides, so we're going to have the x is greater than or equal to negative 11. And looking at what we are going to have for the domain, again, the graphing is going to be optional, but just to give you a bit of a visual layout. So we have for negative 11, okay, with the equal sign, negative 11 is part of the solution. So we'll have a closed point here, and the rest of the set is going to be greater than, so we're going to have an array that is going to go out to the right and running continuously toward infinity. So we have for the domain of the given function f of x, so we're looking at starting from and including negative 11, and running continuously out toward infinity. Now, so those are the results we have for number one. Now for the second item, now we have a blend of a radical and a rational function. And here we have f of x is equal to x minus 3 all over the square root of x minus 4. So for what we have here, okay, so we have f of x, we have x minus 3 all over the square root of x minus 4. And looking at the values for specified inputs. Okay, so we have f of 5. Okay, so we're looking at the y value whenever x is at 5 for x minus 3. Okay, so we have 5 minus 3 all over the square root of 5 minus 4. We have 5 minus 3 is 2. We have all over the square root of 1. Okay, and the square root of 1 is only 1. And 2 divided by 1 is equal to 2. So whenever x is equal to 5, we have that y is equal to 2. And we have for the next part, okay, so we have with the determination of f of 9. For f of 9, okay, so we have for x minus 3, okay, this would become 9 minus 3. And we have all over the square root of 9 minus 4. So we have 9 minus 3 is 6. And we have the square root of 9 minus 4. This will be the square root of 5. And one version of the answer, okay, you can have as 6 over the square root of 5. Okay, but if you had to do stuff like rationalizing the denominator, I'll show you this other possible display. Okay, so again we have 6 over the square root of 5. And if I were to take care of the radical on the bottom, what I can do here is just multiply by 1 in the form of the radical denominator divided by itself. So an alternate display in the answer, okay, we have 6 times the square root of 5, and the square root of 5 times the square root of 5 is the square root of 25, and that goes to 5. So here we have two different ways of saying the exact same thing. And probably for a course like 172, once you get into trigonometry, you'll be looking at eliminating the presence of radicals in the denominator. So I just thought I would go ahead and show you this particular display. And now, for what we have in the case part C, okay, now we have f of x is equal to x minus 3 all over the square root of x minus 4. Okay, now again, the restrictions will lie, okay, with x minus 4 because of the way it is situated. Okay, now first of all, like x plus 11, which is also in the square root, okay, again, x minus 4 cannot be negative. But because x minus 4 is at the bottom of this particular ratio, okay, we also had the second restriction that x minus 4 cannot be 0. Alright, and so where x plus 11 was not in the denominator of a fraction, x minus 4 is. So we have for, again, because of the square root, x minus 4 cannot be negative. And again, because it is in the denominator. X minus 4 cannot be 0. So for categorizing, okay, so can't be negative, can't be 0, so that means that x minus 4 has to be positive. And so setting this up as an inequality, okay, so we have x minus 4 is greater than 0. And so for what we have in the case of x, if x minus 4 is greater than 0, then x has to be greater than 4. Okay, and so we're going to have here with 4, again, without the equal sign, now we have 4 is not included, and for the activity representing the values of x greater than 4, if you were to graph, you would have a ray that would be going continuously out to the right in the direction of infinity. And so we'll have for the domain of what we have for this function, and for the interval notation, so we have going from 4 or past 4 out to infinity. So again, 4 is not included, so we have parentheses placed. Okay, and again, infinity is boundless. So for this radical and rational function, okay, we have once again the domain in the interval notation, again with the parentheses around 4 and infinity. Okay, now for what we have in the case of the next item, okay, and we have just going from individual functions and characteristics. Now we have, again, just crossing over to what we have in lines and linear relations. And we have for the relations, among them we have lines that run parallel, those that run perpendicular, as well as those that do not have either kind of relation. And for what we have in the case of 3, okay, so you're looking at determining the equation in slope-intercept form, okay, of a line that's going to run parallel to the line represented by 2x plus y is equal to 4, and that is going to pass through 3, 3. And so we have in the setup, we have for the given line, again, so we have 2x plus y is equal to 4. And just taking what we have and rewriting, okay, 2x plus y is equal to 4 in terms of the slope-intercept form. Okay, so you have 2x plus y is equal to 4. And if I rewrite this in terms of the slope-intercept, so getting the y term by itself, so we had that y is equal to negative 2x plus 4. And we now have the value of the slope. So you have the value of the slope m is equal to negative 2. Now for the parallel line, now again, parallel lines have the same slope. Okay, so for a parallel line, okay, we had this slope is also at negative 2. And the point through which it passes, okay, we have it 3, 3. Now I'll just do a little bit of color coding here. And just for the backdrop, okay, so we have going through the point slope pathway. So y minus y01 is equal to the slope m times the quantity of x minus x01. So we're going to have here, so we're going to have y minus 3 is equal to the slope m. So we have m at negative 2, and we have times the quantity of x minus 3. Okay, so this is the point slope equation. But now looking for the slope intercept, I can go ahead and distribute negative 2 over the quantity of x minus 3. So I'm going to have negative 2x plus 6. And then getting the y term by itself. And we have upon adding 3 to both sides, so we're going to have that y is equal to negative 2x plus 9. Okay, so again, we had the slope is at negative 2, and for y at 3, left hand side of the equation is at 3, and I want the right hand side of the equation to be as well. So with x also at 3, we have negative 2 times 3 is negative 6, and in turn negative 6 plus 9 is equal to 3, so both sides equal to 3. And for what we have in the fourth problem, so we're looking at a line that's going to run perpendicular to 2x minus y is equal to 4, and that is going to pass through 2, 7. Okay, so you have for the given line, okay, so you have 2x minus y is equal to 4. And if I get the y term by itself, okay, which we're going to have at negative y. So again, moving 2x by subtracting on both sides. So we have negative y is equal to negative 2x plus 4. And so we have in following through, okay, so if I multiply or divide the equation by negative 1, alright, so what was negative becomes positive and vice versa. So we had that y is equal to 2x minus 4. Alright, so for the given line represented by the equation 2x minus y is equal to 4, okay, so we're going to have that the slope m is equal to 2. And for what we have in the case of the perpendicular line, okay, now again, parallel lines had the exact same slope, but for perpendicular lines, on the other hand, okay, the slope values will have an opposite sign reciprocal relation. Okay, so for the given line, we had the slope was at 2, but now for the opposite sign reciprocal of 2, okay, so you're going from a positive to a negative, and think of 2 as 2 over 1, and taking the reciprocal with 1/2. So we have for the slope of the perpendicular, okay, that is going to be at minus 1/2. And again, just a reminder, okay, so again, for the product of the slope values for perpendicular lines, okay, we're going to have to be negative 1. So you have like first slope times the second slope. So you're going to have 2 times negative 1/2. So you have negative 2/2, and so that will go to negative 1. And the point through which the perpendicular line passes, again, is going to be 2, 7. And so we have with the point slope equation backdrop and creating the road to the slope intercept equation. So you have for y minus y01. Okay, so we're going to have y minus 7. And we have equal to the slope m, which we have at negative 1/2. And we have times the quantity of x minus 2. And we have with distributing. So negative 1/2 over the quantity of x minus 2. So we have negative 1/2 of x and negative 1/2 of negative 2. That is going to be a positive 1. And again, isolating the y term. We have for the slope-intercept equation. Okay, so this is going to be y is equal to negative 1/2 of x plus 8. Okay, and you can test this out. So you have the slope at negative 1/2, and with y, just to test the point out. So with y at 7, left-hand side of the equation is at 7, and I want the right-hand side to be as well. So you got with x at 2, negative 1/2 of 2 is negative 1. Negative 1 plus 8 is also 7. Now, looking at what we have for number 5, okay, and we're looking at, again, domains of functions. And in this problem, it says to determine the domain of the following. And we have for number 5, okay, we have that f of x is equal to 2x plus 7 all over x squared plus 4x plus 3. And for the restrictions that we have here, okay, the denominator cannot be 0 in value. So we have x squared plus 4x plus 3 cannot be 0. And looking at factoring, okay, so x squared goes to x and x. Factors of 3 adding up to 4. So we have a 3 plus 3 and plus 1. And neither factor can be equal to 0. So here we have x plus 3 cannot be equal to 0. So we have that x cannot be equal to negative 3. Also, x plus 1 cannot be 0, thus x cannot be negative 1. So again, we have both negative 3 and negative 1 to be excluded. So we have holes at these locations. And just graphing the values that belong in the domain of this rational function. Alright, so we have at the lower end, okay, so we have negative infinity. Upper end we have approaching infinity. So for the domain of the rational function that we have in problem 5, okay, so we have okay, sort of surrounding the exclusion of negative 3. So we have in the interval notation, we have at the lower end, we have values of x, where x runs from negative infinity approaching but not including negative 3. Then we have representing the middle strip. We have those values of x running past negative 3, approaching but not including negative 1. And then for the final stretch, we have those values of x where we have going past negative 1 and approaching infinity. So we have two exclusions from the domain, and because they have two exclusions, we're going to end up with three subsets in the interval notation, that defines this particular domain. All right. And now, for what we have in the case of 6, so we have 2x minus 1 over x squared minus 4, to which we have the function to be defined. Right, so we have f of x, okay, is equal to 2x minus 1 all over x squared minus 4 okay, and a little bit of history repeating in case you have a rational function and the denominator cannot be equal to 0. For x squared minus 4, if I factor, so I have the quantity of x plus 2 times that of x minus 2. And with the factors, so we have that x plus 2 cannot be 0, for which we're going to have negative 2 excluded among the values of x. And as for x minus 2, if this cannot be equal to 0, this leads up to x cannot be equal to 2. And so it's taking what we have here. So we have the exclusions at negative and positive 2. So we have holes at the locations. And so we have with the activity, kind of like what we had earlier, 2 holes, line segment in the middle, and you have continuity out toward negative as well as positive infinity. And so we're going to have for the domain, starting in order from left to right, so you have those values running from negative infinity approaching negative 2. Then we have bypassing negative 2. Then we have approaching 2. We have going past 2. And we have going continuously on out to infinity. For what we have in the case of number 7, again, it says here to determine both the slope and the slope-intercept equation of the line that runs through negative 1, negative 3, as well as 3, 5. Okay. And now for this particular problem, so you have 2 points through which this line is going to pass. So you have negative 1, negative 3, as well as 3, 5. And in the determination of the slope, okay, we want to go ahead and define what our first and second x and y coordinates will be. Now keep in mind, your order pairs will have x in front of y. And let's say that since negative 1, negative 3 is given first, we'll let negative 1, negative 3 be the first set of x and y values. And since 3, 5 is given afterwards, we'll let this be the second set of x and y terms. So we have for the slope, okay, we go with the formula y of 2 minus y of 1 all over x of 2 minus x of 1, to which we're going to have this ratio to define the slope. Okay, we have upon substituting, so for y of 2 minus y of 1, we have y of 2 at 5, and minus y of 1, where we have y of 1 at negative 3. For x of 2, we have at 3, and minus x of 1, so we have the subtraction of negative 1. So here we have 5 plus 3, all over 3 plus 1. 5 plus 3 is 8. 3 plus 1 is 4. And so we have for the value of the slope, okay, this will come out to 2. All right. And just for the slope-intercept equation, you can choose either of these points in the setup. Through the point-slope arrangement. Okay, so you can choose either of these ordered pairs until we'll go with 3, 5, but you can choose -1, -3. Now we have for the point slope setup, okay, we have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. So just looking at the routes here, okay, so you had the slope, again, that was determined to be at 2. And in the case of 5, again, 5 is going to represent the y of 1, whereas the 3 is going to represent the x of 1. And again, you could have chosen -1, -3. And if you did, that works too. So you have y minus 5 is equal to the slope m again, which is 2. And we have times the quantity of x minus 3. So we have y minus 5, and we have with the distribution, we have 2x minus 6. And looking at what we have in the follow through, okay, so if I add 5 to both ends, we're going to have that y is equal to 2x minus 1. And that is going to be our slope-intercept equation. And once again, you can sort of test out the consistency. Okay, so again, this is the slope-intercept equation of the line that is supposed to be able to pass through both of these points. And I use 3, 5 to get to this slope-intercept equation. So just looking at the consistency. So if we have y set to 5, okay, I want the right-hand side of the equation to also equal 5. So with x at 3, 2 times 3 is 6. 6 minus 1 is 5. And also want this to work out for -1, -3. So if we have y at -3, I want the right-hand side to be of the equation to be -3. So here we have x at -1. 2 times -1 is -2. And -2 minus 1 is also -3. All right. Now, for what we have in the case of number 8, okay, so we have, so we got a function whereupon we have f of x is equal to the negative of x squared minus x plus 4. Now I'm looking at, okay, so this is, again, another way of saying y, and I want to find out what y is whenever x is set to 3, and also when x is set to -2. And I'm looking at also the functional expression that results if I change the input from x to x plus 4. Okay, so we have, in this case, so we have with number 8, so we're going to have f of x is equal to the negative of x squared minus x minus x plus 4. Okay, so we have with the input at -3. And let me mention something here. Okay, so the negative sign, read that as -1, like -1 times x squared, because the negative of the square of x is not going to be the same as the square of negative x. If I had the square of negative x, your negative x would be in the parentheses. Okay. So we have, in the case of the first item, let's see, that is f of 3. So we have with f of 3. So I'm going to be taking the negative of the square of 3. And we have minus x, so that's going to be minus 3. We have followed by the addition of 4. Okay, so I got the negative of 3 squared. That's not the square of -3. So we'll be looking at 3 squared is 9, and then the negative of 9, we have minus 9. We have minus 3 plus 4. Now, -9 minus 3 is -12. -12 plus 4 comes out to -8. All right, now, let me mention something. What's going to happen here? Okay, now the domain is going to be the set of all real numbers. Now, the reason, okay, now, let me mention this, okay, for f of 3. Now, let me mention, okay, now let me point this out. The negative of x squared, read this as -1 times x squared. So you got the negative of x squared. Now, that is not the same as if you had the square of negative x. Square of negative x. Okay, that is negative x times negative x. Negative times negative is a positive, so that is going to be positive x squared. So just read this, the ways you could read this, okay, just read this as if it were -1 times x squared minus x plus 4. See, like in the case of f of -2. Okay, so think of it like this. Think of it like -1 times the square of -2. And we have minus -2 followed by the addition of 4. And the reason I'm reading this out as -1 times x squared is that you don't have the negative in parentheses. Now, -2 squared. Now, -2 squared, that in itself is 4. And we have in terms of the follow through. Okay, so you got like -1 times 4. Now, the subtraction of -2. Okay, so that is going to be the addition of 2. Followed by the addition of 4. And -1 times 4, that's a -4. And we got -4 plus 2 plus 4. And you can have the negative and the positive 4 to cancel out. Or you can just read in order from left to right. So I have -4 plus 2 is -2. And in turn, -2 plus 4 comes out to positive 2. Okay. Now, for what we have in the case of the input variable expression, now we have f of x plus 4. And, okay, so changing the input from x to x plus 4. Okay, so the negative of the square of the input. So I still have the negative sign, and we're squaring out x plus 4. And subtracting the input. Now, I subtract not just x, but everything in the input. So we have minus the quantity of x plus 4. And we have followed by the addition of 4. So I got the negative of the input squared. Okay, now, let me mention, okay, so for And I'm just going to work down. Now, on the side here, so we have with x plus 4 squared. Okay, so we have x plus 4 times x plus 4. So we have x squared plus 4x plus 4x plus 16, and we have all together. So you have x squared plus 8x plus 16. Okay, so just sort of carrying over to what we have here. So you got the negative of the square of x plus 4. So you'll be looking at the negative, or the opposite sign of this whole trinomial expression. And distributing subtraction over x plus 4, and go ahead and take out this group of parentheses. So we have a minus x and a minus 4, followed by the addition of 4. And we have in the follow through. So x squared plus 8x plus 16. Again, I'm taking the opposite sign of the square of x plus 4. So this will be negative x squared minus 8x minus 16. And we got minus x. And you can go ahead and cancel out negative and positive 4. And combining the terms, so we have negative x squared and negative 8x minus x. Okay, we have a negative 9x. And again, and for the constants, okay, this will result as minus 16. So we have for the output, okay, we're going to have a trinomial, and all the terms will be negative, where we have minus x squared minus 9x minus 16. And that will be the final result in the output. Okay. Now, just taking what we have now and crossing over to what we have with piecewise defined functions. Okay, now we have with number 9. Okay, so you have a piecewise defined function. You have breaking up into separate categories. Now, so we're looking for, see, f of negative 4. As well as f of 1/2. Also have f of 6. And f of 15. Okay, and okay, now in terms of which of the piecewise defined function portions to use, okay, look at the input. So you have f of negative 4. And looking at the first inequality, so negative 4 is less than 4. So I'm going to use this particular part. So for any input that is less than 4, and negative 4 being among them, the result here is going to be that f of that input is equal to negative 3. So right away, f of negative 4 is equal to minus 3. And for f of 1/2, like negative 4, 1/2 is also another value that is less than 4. And so just like f of negative 4, f of 1/2 also ends up as negative 3. Now for f of 6, okay, now in terms of the inequality statement to which 6 is going to belong, 6 is not less than 4. Now for 6, it does fall between 4 and 8. So it is true if you have the statement that 4 is less than or equal to 6 thanks to the less than part, and 6 in turn is less than 8. And so in terms of how to apply treatment to 6, okay, so you have f of 6 is equal to the absolute value of 6. And the absolute value of 6 is still going to be at 6. Now for f of 15, okay, now 15 is not less than 4. 15 does not lie between 4 and 8. But we do have 15 to be greater than or equal to 8, since 15 is in the greater than portion. And so for any input that is 8 or higher, we're going to have the output to end up at 7. So f of 15 is equal to 7. Okay. Okay, so you have these respective outputs. Okay, -3, -3, 6, and also the number 7. And for what we have in the case of the piecewise defined function that we have for number 10, okay, so we have f of x equal to 4x minus 3, also equal to x squared minus 1, and equal to 2x plus 1. And which one of these is going to apply? This is going to once again depend upon the size of the input. So again, we have f of -3. We have f of 0.6. We have f of 4.9. And also we have f of 5. Okay, so we have with -3. Okay, now -3 is a number that is negative, and anything that is negative is going to be less than 0. So we use this part here. So for any negative value, you're going to have the application of 4x minus 3. So here we're going to have 4 times -3 minus 3. And 4 times -3 is -12. And -12 minus 3 comes out to -15. Okay, now for the input at 0.6. Now 0.6 is a positive value and it cannot be negative, so it cannot be less than 0. Now we do have 0.6 lies between 0 and 5. So you have that 0 is less than or equal to 0.6, which would be less than 5. And so we're going to apply the x squared minus 1 treatment with x at 0.6. So for 0.6 squared, okay, so you have 0.36 or 0.36, take away 1, and so you have, in this case, you have minus 0.64. Okay, and in the case of f of 4.9, okay, now there's a vast difference between the input values of 4.9 and 6. And like 0.6, now 4.9, it belongs to this middle inequality statement, since we have it to ring true that 0 is less than or equal to 4.9, and again that is less than 5. Okay, so just like 0.6, 4.9 is going to receive the x squared minus 1 treatment. So here we're going to have 4.9 squared minus 1. 4.9 squared is going to be 24.01. And take away 1. And so we're going to have another decimal output with 23.01. And for what we have in the case of f of 5. Okay. And here, okay, 5 is not less than 0. 5 cannot be less than itself. And even though 5 cannot be greater than itself, it is equal to itself. So we're going to have the last of the inequality situations to apply. And so with the size of this input, okay, we're going to have 5 to receive the 2x plus 1 treatment. And so we have in the follow through. So we're going to have 2 times 5 plus 1. And 2 times 5 is 10. And 10 plus 1 is equal to 11. Okay. Now, for what we have in the next phase, okay, and again we have operations between functions as well as their domain, okay, and we have looking at what we have given for f of x and g of x. Okay. So we have that f of x is equal to 2x minus 12 and g of x, okay, we have equal to x plus 14. Again, for 11, 12, and 13, the sum, difference, and product functions, all of these are going to have the same domain. Okay, and I'll get to the domain of these in just a moment. Now, looking at the outputs specifically, so for f plus g of x, we're looking at the sum of f of x and g of x. Again, f of x, we have 2x minus 12. And g of x, okay, so we have x plus 14. And upon removing the parentheses, so if I take the sum, okay, so I have 2x minus 12 plus x plus 14. So you have 2x plus x comes out to 3x, and negative 12 plus 14 comes out to 2. So for the sum of f of x and g of x, with what we have assigned for f of x and g of x, okay, we have it 3x plus 2. Now, for the difference between the functions, so you have f of x minus g of x, and here we have the quantity of 2x minus 12. And we have minus, okay, the quantity of x plus 14. So we're going to have 2x minus 12. And then with x plus 14, subtraction will be distributed. So we have minus x minus 14. And we have 2x minus x comes out to x. Negative 12 minus 14 comes out to negative 26. Okay. And for the product function, okay, so we're looking at f of x times g of x. For f of x times g of x, okay, so we have 2x minus 12 times x plus 14, and looking at the attainment of the product, so we have 2x times x is going to be 2x squared, and I'm just going to go ahead and gather the outside and the inside terms. So 2x times 14 becomes 28x. In side product we have negative 12x, 28x minus 12x. This becomes 16x. And for the last product, okay, we have for negative 12 times 14, this is going to be minus 168. Now, again, the sum difference in products will have the same domain. And the domain for the sum difference in product functions, okay, they'll be formed by combining the restrictions of the immediate functions involved. Okay, so for f of x equal to 2x minus 12, we do not have a fraction or an even root radical. So f of x has no restriction. Also, for g of x, like f of x, okay, we have a linear expression, no fraction, no even root radical, and so we have also no restriction. And guess what? Since there are no restrictions between f of x and g of x, there are going to be also no restrictions for the sum, difference, and product functions. And so for what we have in the case of the domains throughout, again, the sum, difference, and product functions will all have the same domain. And since there are no restrictions, it's going to turn out that for the domain of all three of these operations, we're going to have the set of all real numbers. And once again, so the sum, difference, and product function will have the same domain, but now with the quotient function, okay, again, this could be a function that will have a domain that is different from the first three operations. Now, for f over g of x, okay, this is equal to f of x over g of x. And just filling in, with f of x over g of x. F of x we have at 2x minus 12. And g of x, okay, we have with x plus 14. This will be the resulting quotient function. And now f of x and g of x, again, individually, neither one has a restriction, but for the quotient function, we have g of x situated on the bottom. And so we have not just g of x, but the reciprocal of g of x. So we have a restriction that is imposed, because now g of x is not allowed to be equal to 0 because of where g of x is placed. So we have the x plus 14 cannot be 0. So we have the x cannot be equal to negative 14. Again, so we have only 14 is excluded. Negative 14 is excluded. Again, so you have an open circle, and just for the activity, and everything is going to be either greater than or less than negative 14. And so for what we will have, okay, for the domain of this function, okay, so you have those values of x less than negative 14, along with those values of x that will be greater than negative 14. So you have one exclusion, and in the interval notation, can we have two subsets in the formation. Okay. All right. Now, in the crossover to where we have the composition of functions and where the domain is concerned, okay, guess you can say that we'll be kind of hitting a reset button. Okay, because with the domains of the sum, difference, and product functions, you're just automatically combining the restrictions for the immediate functions involved, and in the quotient function, you might have a denominator that's creating a restriction. Now, for what we have in the case of the composition of functions, again, we have f of x is equal to 2x minus 12. And we have that g of x is equal to x plus 14. And now for what we have in 15, okay, so if we're looking for the composition whereupon we have f composed with g of x, and we have in the compact functional notation, so we have f of g of x. Okay, and so we have the output function, okay, to be in line with f. We have f of the input is equal to 2 times the input minus 12. And we have in the follow through, so we have f of g of x. Okay, so we have f of the input, so that's going to be 2 times g of x followed by the subtraction of 12, and then specifying what we have for g of x. So we have 2 times g of x translates to 2 times the quantity of x plus 14 followed by the subtraction of 12, and we have upon distributing, we have 2x plus 28 minus 12, and so this will come out to where we have 2x plus 16, and that'll be the result for what we have in this composition. And where the domain is concerned, again, you're looking at the restrictions, if any, of the input function as well as what we have for the output. So the input, okay, so you have input, we have at g of x, and g of x is equal to x plus 14. And since we don't have any fractions or even root radicals, okay, there is no restriction. And for the output, okay, we have at 2x plus 16, and like g of x equal to x plus 14, okay, we don't have any radical or fraction, so you have no restriction, and so between the input and the output, there's no restriction at all. So for this particular composition of functions, we want to have for the domain the set of all real numbers. And if I reverse the order of the functions, okay, and we have for the next composition, okay, so I have f of x equal to 2x minus 12, and g of x equal to x plus 14. So here I'm going to have g composed with f of x. So I'm going to have g of f of x Okay, so this time we have the outside function to be at g. And again, g of the input is equal to the sum of the input and 14. Now with the input at f of x, okay, so this can be f of x plus 14, and f of x we have at 2x minus 12. We have adding 14. And what's going to happen here, so we come out to 2x, and minus 12 plus 14 comes out to a positive 2. And so that will be the resulting composition here. And in looking for the domain of this composition, so we now have, once again, we have with the input okay, so we have f of x is equal to 2x minus 12. Okay, there's no, again, no fraction, no even root radical, so we have no restriction. And for the output, okay, again, which we have at 2x plus 2. Again, we have a direct linear expression once again, so we have no restriction. So while we have a different composition in number 16 relative to what we had in number 15, okay, again, we have no restriction at all. So that means that, once again, for the domain, okay, that is going to be the set of all real numbers. All right. Now, for what we have, just kind of taking a little bit of composition. Okay. Now we have just in the determination of the domain, and we'll look at what we have for, let's say, just the first three functions, the sum, difference, and product functions. Now we have two rational expressions. Okay, so we have f of x is equal to 3 over x minus 1, and g of x is equal to x all over x plus 12. And so I'll do it this way. All right, so you have f of x equal to 3 over x minus 1. And again, we have for g of x is equal to x over x plus 12. Okay. Again, we're looking for the domain of the sum, difference, and product functions for starters. Okay, so we have, first of all, for f of x equal to 3 over x minus 1. X minus 1 cannot be 0, so x cannot be equal to 1. And for g of x, then we have x over x plus 12. And to keep x plus 12, the denominator, from being equal to 0, we had that x cannot be negative 12. Okay, now for the sum, difference, and product functions, again, we need to be able to work exclusively with, or I should say, work with f of x and g of x. So to be able to work with f of x, I cannot have x to be 1. And to also be able to work with g of x, x cannot be allowed to equal negative 12. So in terms of sort of sizing things up, okay, so for the sum difference in product functions, we have these two exclusions. Again, we have with negative 12 and 1. So we have negative 12 excluded. Now 1 is excluded. Okay, so for the sum, the difference, and the product functions, okay, you have, again, these two exclusions. And so for the sum, difference, and product functions, okay, we have for the domain, we have values of x less than negative 12. Okay, so we have, in this one case, we have values of x less than negative 12. And then we have, in between, have those values going past negative 12, approaching but not including 1. And then we have those values, okay, that will be greater than 1. Okay, and so, again, the sum, the difference, and the product functions will all have the same domain. Okay, and so okay, so for the sum, difference, and product functions, okay, these will be the same domain, and okay, and we'll be looking into the other parts, including the second part of the test 2 review, and now we'll get into the quotient and the composition of functions